All right, good afternoon. Welcome to today's webinar, which is a live demonstration of Stampack forming simulation software. The webinar today is presented by Accurate Die Design Software and hosted by Metal Forming Magazine. I'm Brad Kubin. I'm the editorial director of Metal Forming Magazine at the Precision Metal Forming Association, and I'm very pleased to be the moderator for today's session. So let's go ahead and begin today's webinar. Our presenters today are Ray Prober, president of Accurate Die Design Software, along with Josh Hellman. Josh is a sales application engineer with Accurate Die Design. And they are joined today by Dr. Luca Hornung. He is the co-founder and R&D manager at Stampack. So these gentlemen are going to demonstrate for us the workflow using Stampack, showcasing in particular the benefits of the ability of the software to have both a shell solver, say that 10 times fast, for extreme speed, and a solid solver for extreme accuracy. So without further ado, Ray, go ahead and take the floor.
Thank you, Brad. So Dr. Hornung is going to be starting the presentation with a PowerPoint presentation, as you can see on your screen. And after 20 minutes or so, our Josh Hellman will take over and do a demonstration of Stampack. Josh joined us on January 2nd of this year, and we're really thrilled with how much Stampack has helped him get up to speed and understand dies and etc. So anyway, enjoy the presentation, and let's get started. Go ahead, Luca.
Hello and welcome everybody from my side to today's webinar. So today we speak about solutions for people that make metal stamping. And what you will learn today is interesting for people that make progressive dies for electrical connectors, medical parts, to normal size progressive dies, up to really heavy stuff that is single hit line dies for example, drug parts. So the range of application of our software is from about 0.1 millimeter up to about 10 millimeter thickness. Before we start with technical details, I will introduce you who we are. So what is Stampack GmbH? Stampack GmbH was founded in 2018, and we could grow our company to now 17 employees. We sell our software solution worldwide, and we grew our customer base to all in all 145 software customers. In 2023 at FabTech in Chicago, we launched our software to the US market together with our reseller Accurate Die Design Software, and that's why we are here together to present our solutions. And since then, we have grown a very good customer base in the US. Maybe the most famous of our customers is Cosma Die Technology, that is a Magna subsidiary in Detroit. But also beside this, things are going really well, and the US is our largest growth market in the world. What is the purpose of our software? We want to make a simulation software for the tool designer himself. So this means our software should speak the language of the tool designer. So we do not make software for academics or material scientists. We make software for people that come from the practical life. Equally important is that Stampack should provide fast computation and reliable results. And during my presentation, we will speak more about this because we have technology that is dedicated for extremely fast computation, and we have technology that is dedicated to reliable results. And finally, I mean, that's also very important, Stampack should be affordable for every tool shop and every engineering office in the world. So why do we need simulation software? To explain this, I want to show you the process chain in metal stamping when you have simulation software. So typically, you start with a product design, and based on the product design, yeah, you have to make the process design. That is in progressive dies, the strip layout. And if you don't have simulation software, then you have, in the end, you have to make a tryout in steel. So you have to construct a tryout tool, you have to go to the shop floor, and you have to perform a tryout. And the nice thing when you have simulation software is that once you have the strip layout, the designer himself, before the actual tool construction, he can perform the tryout in the simulation based on the strip layout. So one person is iterating in a very fast, in a very agile loop, and only when he's happy, then the tool is constructed, the tool is assembled to the press, and we go to production. So it's a very fast iteration loop, and you have great savings in time and money because it's much faster to make a tryout in software, yeah, that is typically about 1 day, than to make the tryout in hardware, which can take weeks and weeks. What kind of processes are supported by Stampack? Yeah, basically, I would say everything running on a press. So progressive dies, line dies, transfer dies, no matter, prototyping tools, hand insertion tools. And just to give you an overview about the processes we cover, you can perform classical stamping, deep drawing. You can also make really heavy ironing and compression along the thickness. And Stampack also supports trim optimization, spring back compensation, and what I like best, you can check your tolerances in Stampack. And before we start to go to the technical details, I would like to simply give you an overview how the software can help you in your everyday life. So first of all, the software shows you whether your part is feasible, yes or no. So when you have a crack in a real part, then the software shows here a red area in the same spot. Even better and even more important is the software can tell you how far you are away from failure. So typically, well, we see here a number between 0 and 100, and material failure is at 100%. So on the left-hand side, for example, simulation predicts you a maximum value of 99, and 99 is so close to 100, and then you know immediately, okay, it's not safe to go to production because a slight change in the production conditions will lead to a crack. On the contrary, on the right-hand side, the maximum value is 81. And when you have maximum value 81, then there is a lot of margin left in your process. So it's not risky at all. It's perfectly safe. And no matter how the conditions change in production, you have a safe process. And even better, if you make progressive dies and you have so much margin left and the process is so uncritical, then you can try to reduce your process design maybe by one station, and you can try again. And maybe in this, maybe you reduce the by one station, and there is still some safety margin left, and then you saved already a lot of money. What you can also see in Stampack is how the wrinkles appear during the process. So we have here an embossed sheet. So that is what people use to make heat shields. And here you see in Stampack we simulate including the embosses. And during the process you see very well how the wrinkles appear. And then in this kind of process, wrinkles are allowed, maybe in some other processes not, but they are predicted by simulation, and then you can judge whether you like the wrinkles or not. So in this case, it's allowed, but maybe in others not. one of the most important features for our customers is the so-called tolerance check, because tolerances are everybody's problem. In the end, at the end of the day, the question is not always to make a feasible part, because maybe you know how to do it, but the question is, am I in tolerance, yes or no? For example, in this round drawing part, tolerance was plus minus 0.1 millimeter, and then you see immediately, okay, in this area, I'm out of tolerance. In this area, I am out of tolerance. I have to change something in the process design to come back to tolerance. Very much connected to this, and I think this is also everybody's problem, is springback, because springback is a typical thing that drives you out of the tolerance. And so Stampack predicts springback for you, and Stampack compensates the die surfaces so that you can come back to tolerance. And later on, I have an example for you so that you can get a feeling for what springback compensation does. Also very important, and this is especially for people that make processes with a lot of coining, you can predict the material flow in Stampack. So this is a very easy coining, yeah, but when you see how the material is compressed and then it's squeezed out, and in this kind of processes, it's very difficult to predict where the outline will be. And the software predicts you the material flow, and with our technology for trimline development, the so-called trim optimizer, you can the initial outline is changed automatically, yeah, to get the outline finally in tolerance. So here the user imports a target part. You see it here in red, and in the first iteration you see here is too much material, and here is not enough material. So here we have to add material to the initial blank. Here we have to remove material from the initial blank. And what Trim Optimizer does, in a fully automated cycle, in several iterations, it optimizes from here until you are perfectly in tolerance. So now you have a feeling for what Stampack is doing. And now I would like to come back to the aspect fast result and reliable result. And we will speak more about our technology, that is here the shell simulation and the solid simulation. So with shell simulation, I mean the blank here is in the mid surface of the sheet, and it's a two-dimensional surface, and it's covered by triangular elements. And this technology is very good because it's extremely fast. So you can, no matter how big the part is, you can make simulation in 5 minutes, 10 minutes, 15 minutes. And also, the quality of results is really good when you have thin sheets with larger radiuses, and also for thicker sheets, then still it's a meaningful good first impression, so you can judge, for example, very well about feasibility. And on the contrary, we have the solid simulation. Here you see the sheet is a three-dimensional object. So it's here a hexahedral mesh, and let's say we perform the simulation very physically with contact with the die surfaces on top and bottom side. And this technology gives excellent quality of results for all kinds of parts. And the main benefit is that stresses and strains along the thickness give a very good precision, and you have really a wonderful resolution all over the thickness. Especially when you have thick sheets and small radiuses, this is mandatory to finally validate in the solid simulation. And a nice plus is that surface deformation and tool marks can be shown very well with solid simulation. And maybe you ask yourself now, which of the technology do I need to be successful? And the answer is you need both technologies. So our typical workflow is whenever we start with a process design, we start with a shell simulation to get rid of easy defects. So for example, here, the stretch web is stretched too much. Yeah, and you see immediately, okay, this can never work, so we have to change something. And this is very typical, and we make several iterations in our process design in shell simulation until we reach a point where we are happy with what we see in shell. And then we make the next step and say, okay, now we switch to solid simulation, and in our software you can do this with one click. You can change the entire setup to solid simulation, and then we validate the part in solid simulation, and we make our fine-tuning, which means we see surface defects. We can make our spring back compensation because spring back prediction is much better in solid. We can spot the dies, so we get a new level of accuracy in our solid simulation. And then maybe we make one or two more iterations in solid, and finally the process is validated in solid, and then we can go to production. So you need both technologies because in the beginning you want to be fast, and the more you come to the end, the more precise you want to be. I think I should explain a little more in which cases solid simulation is more powerful and more precise than shell simulation. Just to give you a feeling, I start with this quite thick sheet. So I think it's 3 millimeter, 3.5 millimeter thickness. And you see here how the shell simulation looks, how the solid simulation looks, and how the reality looks. And then you see, for example, when you compare the corner here or this corner, then the solid simulation is really very physically. So I would say when you are beyond 2.5 millimeter thickness, then solid simulation is much more precise. A very important effect I want to show you is the simulation quality in case of thickening in the sheet and compression later on. And to highlight this, I have here a quite easy progressive die from one of our customers. And what happens here, so I made here a cross section, and this is a solid simulation. And you see here in this focus on this area, you have some thickening. So in the beginning, we had 2 millimeter thickness, 2 millimeter thickness. And then let's say here we get some thickening and we compress the sheet at the very end. So you see here quite well what I mean with contact on bottom and how wonderful it's compressed. But let's compare now shell and solid. 0.75 millimeter before the press closes, you see shell and solid have comparable results. Yeah, so the sheet is quite thick now here in this very locally, but now the press comes down, and then you see 0.35 millimeter before the press closes. The shell cannot really show compression because the contact is not physically well done, whereas the solid simulation compressed very well to 2.36 millimeter, which is the remaining stroke. And then at the very end, when the tool is closed, you see a huge difference between thickness prediction in shell and solid. And shell is here, in this case, totally wrong, whereas the solid also simulated the compression very well. And the main point is here, for spring back prediction, this hit at the very end plays a huge role. So in shell simulation, software predicts 4 to 6 millimeter. In solid simulation, the maximum spring back in Z direction is 2.7 millimeter. And this is because we introduce a lot of plasticity and stretching just at the very end of the simulation. And it turns out that in this particular case, the solid simulation was really precise. I think the real spring back was here 2.79 millimeter. So the solid simulation did a fantastic job here. And if you think that you want to compensate, yeah, if you compensate with the wrong values, you will never come to a good solution. So that's why we say whenever we have more than 10% thickening in a part, then you should finally validate and compensate your spring back in solid, because prediction quality is much better. A nice benefit is the surface quality. So this is a real part from one of our customers, and we see here the so-called blank marking. And just take a second to check how wonderful we can see here the areas that have where you see the marks coming from the friction of the tool with the sheet. So here you get a feeling what I mean with a physical contact. Let's speak once more about springback compensation. So I have another example for you with me. So this is a typical part where springback is difficult. Yeah, you see here, this is the sheet after springback. This is the sheet before springback. So the part is maybe 600 millimeters long, I think. And we have here in this area, I think 3 millimeters deviation to the nominal. And what happens now is in the initial situation, yeah, when you just took the first attempt with the die surfaces, then we see here the picture of our tolerance check, and you see here in this area, for example, we are far away from the tolerance. Tolerance was here plus minus 0.5 millimeter. We are about 3 millimeters off. So this cannot be. And then our springback compensation takes the die surfaces, compensates the die surfaces, and even, I mean, here you have vertical walls, and we also compensate perfectly in the vertical walls. And after the third iteration, you see here in the color map, we are perfectly in tolerance. So here maybe we are 0.4 millimeter out of tolerance, and here we are about 0.1, 0.2 millimeter out of tolerance. No, sorry, we are away from the nominal by 0.5 millimeter, 0.4, 0.1 millimeter, but tolerance is 0.5 millimeter, so we are perfectly fine. So iteration by iteration, we compensate the die surfaces until we are close enough to the nominal part. Before I hand over to Josh, some more examples for trim optimizer. So here, this is a typical automotive example. We see here that we have too much material, 3.2 millimeter away, from the target line, and in 4 fully automatic iterations, we could change the initial outline until being 0.15 millimeter away, which is really precise for this kind of part. And this technology not only works in thin sheets, but it also works in quite heavy stuff. So we see here a 4 millimeter thick part, and this is now here a solid simulation, and we have a lot of material flow here, and also some coining in the walls, so the material is squeezed down. And here, in the initial situation, we see that we don't have enough material, so it's required to add more material to the initial blank, and then in 3 iteration, we came from 2.4 in the beginning to about 0.5 millimeter away from the target line. And after 6 iteration, I was really, I was really pleased to see that we came close to 0.04 millimeters, which is extremely accurate. I mean, tolerances in this kind of parts are typically 0.15 millimeters at the boundary, so it's perfectly well done. And finally, because I really like this example, the coining for electrical connectors. So we see here again, material is coined, it's squeezed out, and yeah, if you have if you would go with this part, yeah, you would need an additional cut. But look what Trim Optimizer did in five iterations. So it designed the initial blank in a way that you are away from the target line, 0.02 millimeters. So again, extremely precise. And the benefit for you is, yeah, that you don't need a cutting station anymore. It's completely saved. Okay, so far so good. Thanks a lot for your attention from my side. I hand over to Josh. More examples can be found at diedesignsoftware.com. Please visit the webpage and check some wonderful application examples. As I said, a wide range of application examples, from electrical connectors to very huge dies, from automotive to trucking components. Feel free to go there and learn more. Thanks a lot from my side, and I hand over to Josh.
Perfect. All right, thank you, Luca. All right, what we'll be doing in the next section here is just reviewing a full die design that we're going to do together here. This is the progressive die that's already been designed on the right-hand side. And what we're going to do is we're going to take this part that's going to be made out of 304 stainless, and it's going to have general tolerances of plus or minus 10 thousandths. And for what we'll show here within inside of the Stampack software itself, what you'll see is that in your actual CAD design, you'll have the full 3D component, but with inside of Stampack, we only care about having just the active surfaces that are going to be actually touching the tooling to the blank and actually forming the geometry. So when you see the geometry inside of Stampack, that's what we're actually working with here. So what we'll do is we'll open up our software, and at the very top of the screen, you can see that we have a nice little progress bar, and it starts with the Start tab where you can go ahead and save and open up any other projects you might have. Then you can define the blank, set up any of the operations and stations that you've done in your die, go to Calculate, and then view the results. So right away, we just have this set up to being 2.5 inches for our total press stroke. And we'll define this thickness to be 0.0747. And then the next thing we can do is we can set up our material. So Stampack has a very, very inclusive and wide variety of materials that you can choose from. There's titaniums, brasses, coppers, aluminums, stainless steel, multiple different types of high strength carbon steel, whatever you're looking for. In this case, we're going to be using 304 stainless. So let's select that and apply that to our file here. And then we'll specify our blank geometry that we're going to be working with. And I'll bring that screen over so everyone can see that here. And for this, we bring this in just as an IGES file. And this has the whole outline of the blank that we're going to be actually working with while we're here inside of Stampack. And we'll set this to an automatic mode, so we don't have to set anything. As far as the mesh size goes, Stampack is really, really good at this actually, where you don't need to actually type in and specify any of the mesh. The only thing that you would ever really need to put in here is just that minimum radius of curvature, and then Stampack will take that information and it'll generate the correct amount of mesh that you would need for this file. And another thing that we'll be doing is we're going to be applying some symmetry to this file. We're going to be doing that along the Z and X direction. And this is because this is actually a 2-out die, and what we have here is just 1/2 of this file. And to save on simulation time, you don't have to do the entire file to simulate it. You can just apply some symmetry and then let the software do the rest. And another thing we'll be doing here is we're going to be adding some strip conditions, because the rest of this connector here is going to have, obviously all the other stations that are being formed before and after this. So the material here isn't going to be moving along the X direction. So we'll go ahead and get that fixed in place now. There we go. And now we can go ahead and continue on to defining our processes. So the first thing that we'll do here is we'll import all of our tooling from our software, from whatever CAD software you're using. And this is how it looks when it gets imported inside of Stampack. You'll see that everything gets a color assigned to it. So it's a little easier for you to tell the difference between the components. And in this case, this LF, this is going to be our lower form. And again, it's very easy to use this with inside Stampack. You could just drag and drop it and select whatever kind of tooling that this is going to be. In this case, that's going to be a die. This upper form is going to be a punch, so we can drag and drop it as so. And then lastly, we have our pad here. And so this stripper pad, we're going to be adding that to our top press ram as a pad. And that's going to allow us to set an initial and a final force, since this is going to be springed here. So we'll set that with an initial force of 4,000 going up to 7,000 pounds. And we'll give this a stroke of 0.625. And this is also going to have a bottoming block applied to it. So as soon as this as soon as the cylinder stroke hits this 0.625, it's going to have the full force of the press going with it. And to validate and make sure that we actually have everything set up here, we can use our kinematics. And you can see in real time just how these components are going to be simulating together. So now that that's done, we can add a new operation, and we're going to be moving our component now to the next station. And so we'll just be moving that by 5.25 inches to the left-hand side, since this is this die is feeding right to left. And then we'll add another operation right after for forming. And once again, we'll go ahead and import our other operation. And get these files added in. And now, again, just like we did before, we can just simply drag and drop these files in wherever they're needed. So I'll bring in both of these upper forms. And then this lower form, we'll bring that in as a punch. And then finally, we have this die pad again, so we'll bring that in. And this one is going to be set to 5,000 pounds in the initial, and then it's going to end with 8,000 pounds. And it'll have a cylinder stroke of 1.25. And once again, this one's also going to have its end position blocked by a bottoming block. And then we can add another positioning as we move this one station over, and automatically it'll already copy over whatever amount we moved the last one by. And now we can go ahead and add a cutting operation. And for this, we can select our cutting geometry. And this cutoff punch is just going to be a square cutoff punch. So that's all the information that's needed at this point here. Then we will also need to specify what area of this cutoff punch we're keeping and what areas we're getting rid of. So we'll go ahead and select that now. And with that, everything should be set up for what this is going to look like. So we can go over to our calculation tab here, and we can start the simulation. And right away at the top, we have this nice little call out that tells us exactly how far along the simulation is. So right now, it's working on calculating everything for this operation 10. Then once that finishes, it'll go to the first positioning, to the next forming operation, and then finally it's going to end with that cutting operation. And once any of these do simulate, you don't actually have to go back and re-simulate if, let's say, we made a change to our cutting punch. If we change some of the geometry here and we now need to go through and rerun it to see what the final geometry is going to look like, you don't have to re-simulate the entire thing. You only need to re-simulate from the point that you made a change on and anything that might be after it. So it definitely saves a lot of time if you do have a lot of design changes that are going on in the press in any later stages, because I know that can be a big pain point for some. Well, while that's finishing, we can go over to the results tab. And just as these are finishing out, you'll actually see these automatically populate here in the operations that are already posted to our results. So right now, operation 20 is working its way through currently. And then there you can see that position and that final cutting just came in as well. So we can go ahead and we're going to look at all of those results together. And this is what our final part looks like after all the simulation is done. And so what we'll do here is we're just going to go ahead and play the animation so we can see how this material looks as it's getting formed. So here, as this front half is getting formed down, you can see just how this gusset is applied and how everything moves together. You can either hide or show these components. So here, as these side walls are getting wiped down by the forms here on the end. And then finally, you can see that the rest of that strip is cut away and we're left with just our final component. So to quickly validate this part, we can look at some things like thickness. With a part like this, we don't have any thinning that is going to make this part come out of tolerance. In this case, we don't have anything that's even over about 18–19%, so we should be all good there. If we look at safety zones, just to see if we have any cracks that are forming, nothing is showing in red, everything is showing safe, and a little bit of compression here on those legs. And then the last thing that we're going to do is just a graphical verification that everything looks good here. And if I reposition camera just a little bit, you can see that we have this deformation that's coming right down the side here. And that's because that first operation is forming across the entire length of this geometry and not just that middle section. And if we compare this to what we actually have in the real life part, you can see that that's happening the exact same way. So this was something that wasn't caught the first time around. And when this file was created, you can see that it was causing a lot of severe galling that was actually happening on those outside sides. And if you did want to see if there was going to be any kind of blank marking going on, we can actually bring that up here. And this is every place in red that you can see. This is where we should see those tool markings, and that's pretty much exactly what we're seeing in real life as well. So given that information, we know that we need to make some changes, so that's what we're going to do now. So we're going to go back over to our process tab here. And we're going to make an update to our first operation so that we're not forming all those areas. And this is going to be our second revision to this file. And here are those three new geometries that are coming from our CAD system after we're aware of this issue. And it's very simple to just replace these. Again, you can just drag and drop these right over top of the existing ones and they'll replace the files. So we'll get these all replaced right now. There we go, and you can see that now this is forming around just the center portion, and it's not forming around those legs. It's going to give us some of those problems that we were seeing previously. And so we'll go over to our cutting operation as well, because now that we've confirmed that, that graphically everything should be looking correct now, and there wasn't any problems with safety zones or thinning. We want to now take a look at our trim and see if it's actually meeting tolerances and start going from there. So what we're going to do here in our last operation, and you could do this in any operation as well, but we'll do it in our last one here, is we're going to select a target, and this target is just coming directly from our CAD system. So this is just the CAD version of the output of this file. And now that that's all set, we can go ahead and recalculate this once more. And yep, we'll recalculate everything because we did make a change to that very first operation. And another thing we can do here while this is working its way through, we can open up our process information, which is going to give you real-time information as far as what's going on with the simulation. So you'll see right now it just updated, and all of these line items here are going to tell you for this middle section how much time has elapsed. So this is really useful if you want to know, how long are you into this exact simulation, or maybe just this exact operation. So right now you can see that we just got some information as far as that positioning that was done. That didn't take any time at all, actually. It was just 0 seconds. So very, very quick. And over on this right-hand side, you can actually see the press stroke that's left. So if you don't know if you're right at the very end of a simulation, or if maybe you're right at the very beginning, this is going to be a really good indicator, so you kind of get a good understanding of, are you almost done or not, and just how much is actually left here. So again, that's just about finished out. So we'll go and jump over to our results. And while that's actually working, we can load up our operation 10 here and just take a closer look at what the final geometry looks like here. And we just got notified that the simulation finished. And we can see that, yep, now that we're no longer forming those edges, that we're not getting any kind of lines going across these to start with, so we should be good. And we can load up that very final operation once more. And we can graphically compare this once again. And yep, no more lines are coming in here. So that galling should be fixed, and we shouldn't have a problem with that anymore. So the next thing we can do is we can take a look at our target geometry compared to, in gray, what our simulated geometry is. And already you can tell that we have quite a bit of issues. The physical geometry that's getting formed by simulation is kicking back towards the back end of this quite a bit. And if we want to know exactly how much, we can actually just go into our measure command here. And you can do this at any point in your simulation, measure between any components. But here we see that this is 25 thousandths. And if you recall, this file had 10 thousandths as its limit for its tolerance. So right now, this part is out of tolerance. And once more, if we do go back to what the final product looked like after all this was first done, you can see that the geometry here is not that great. This is definitely not a true radius. We're having a lot of geometry pulling in and pushing out where we don't want it. So for that, it's very, very simple to set this up inside of Stampack here. We can just simply go back to our process tab and turn on our trim optimization. And now we'll get an extra tab that we can use. And here we'll go ahead and select the target file that we want to use for this right away. And if I zoom in, you can see a green line here. And let me go ahead and turn this other CAD geometry off. And you can see the green line is the target for where we want this trim to come up to. And that's right in line with this inside edge of our original CAD geometry. So because that's the inside edge, that's the bottom face, we'll go ahead and change this over to bottom. And then we'll leave at the very end here, we can change our max iterations that we want to have run. And we'll leave that at 5. And for the max deviation, we could change this to the 10 thousandths. And right after maybe 2 iterations, we would definitely hit that 10 thousandths. But we want to see just how accurate we can get this file to. because you always want to put in whatever accurate information you can in CAD in case the real world, when you go to actually form this, if there is any, deviation as far as, maybe something was grind a little bit deeper than you would have liked. So because of that, we'll change this to 1,000th, and we'll see just how close we can get this. And rather than recalculating this file, I do already have this calculated out, but we would be all set there after setting up just what we did within the trim optimizer. And so here you can see a list of all the iterations that were calculated. And if we look at the results of this, over here in red, this is what our final blank is going to look like. And if I come over to the side here to look at the difference between the blue and the green again is our target geometry, and the blue is our original geometry. So if I back this up to the original first iteration, this is what it looks like before any optimization has occurred. You can see that that blue line is a lot further over to the left-hand side here. And as we drag this bar through all the iterations that Stampack has done, you can see that that blue line makes it all the way so it's writing right on top of the green. And we can actually see that we have an average deviation of less than 1,000th here. And the maximum deviation at any point on these lines is only around 4,000ths. So we definitely have this within those original 10,000ths, and we should be all good from here. Once this is finished, we can click this button here to update our main project with this brand new blank that it's going to generate. And we can do that now. And then now with our new blank information, we can also come over, recalculate that, and we can set our global strip conditions up again. So let me do that now. There we go, so the strip is connected again. And then the other thing we're going to do is we're going to add one more operation so we can start looking at springback, since springback is going to be the last thing we're going to do with this file, and see if we can find any problems. And for this, I'm just going to simply add the operation. We don't have to set anything up here in order to see some of those results. And the last thing, you can see we still have this optimize tab here, so we'll go ahead and turn the optimization off and run this once more. Up at the top here, you can actually also change where you're going to be running these files from up until for the operations. So if you didn't want to simulate all these operations, maybe just one, maybe we only wanted to see the changes after operation 10, you can always just simulate that. You don't have to simulate everything that's in here. Another really handy thing is while this is actually running, that's actually running in the background, and it's not doing anything for our interface here that we're actually working on. So as this is processing through, I could always jump back here to our processes. We could start adding new operations. So it can be very, very slick when you're actually going and making these changes in real life. After you had just made maybe a change to the operation 10, just like we did at the beginning, we could have simply solved that first operation while we're still setting up all of the other operations. So it can be a very, very big time saver where you don't actually have to go and make so many changes and constantly be waiting on the tool. So if we come back here to calculation, you can see we're right on operation 20, that's solving for right now. So let's go over to our results. And it looks like operation 20 finished. And now we have our springback results all ready for us. So let's go ahead and load those up. And I'm going to look at it from the front here. And already you can see that that's some pretty severe springback. So if we go ahead and play the animation here, so our file springs back on these legs quite a bit more, and we only have that 10,000ths to work with. So let's take a look at what that looks like when we just compare it to the initial geometry. And yeah, those legs are almost moving an entire material thickness away. If you did want to know exactly how much, we could show that information, or you could also load in a copy of what your of what your CAD geometry looks like, and you can take exact measurements between those. So when you do see that information, you can always look and see that specifically. But if we want to go ahead and make a change to this file, I'll load up our pre-solved version of this as well. So this is the CAD geometry that we had actually brought in here. So what we're going to do to fix the spring back that we're seeing is we're going to actually simulate rocker forms that are coming down, interacting with slopes, and rotating about an axis that's in here. So inside of Stampack, you can set up all these different kinds of relations between your components. So you're actually, being able to fully simulate whatever you're setting up in real life. And after we implement files like this, let's go ahead and load up our final results. And we can see exactly what we're left with. So let's go ahead and play this very final spring back that we have here. And if I compare that to what the original geometry is, you can see that we're coming right back to where we need this. And we're within the 10,000s that we have here. And the way that those rocker forms are actually developed was multiple different iterations of me running this software in order to know exactly where I need to position those rocker forms, how far they need to come down, how far they need to push in. So rather than having to try this many different times in the press, you can just simulate it once, know the geometry that you have to do, and work with exactly that. All right, and that is everything I have for the full development of this die here.
Josh, could you show us how long the trim optimization took?
Yeah, I sure can. Let me go ahead and open.
We had opened that when it was already solved before. It'd be nice to see how long we would have been sitting here.
There we go. So this one actually, let's see, I had finished that one at 13:15. And if we looked when I started this simulation, so that took around 13 minutes for this. When you do trim optimization, since it knows it's going to be a little bit longer of solve time, since you're calculating the whole thing multiple times, it'll also tell you the exact time and date that everything was done at.
So that's clock time. Okay, that's the date and time.
Yeah.
Okay.
Yep, that is correct.
Cool.
So yeah, this one took about 13 minutes to solve this, and that did it through. Go back here. So we did 5 iterations, but we also had to start with your initial. So this was solving this 6 times in a row, and the software was automatically making change to that blank geometry, then redoing it. So all that in 13 minutes.
Very cool. Thank you.
Perfect.
And I guess with that, we're ready for questions. Brad, do we have any questions coming in yet?
We do, and we've got a couple minutes left. If anybody wants to ask these guys questions, go ahead and use that question panel on your go-to screen. A really nicely detailed presentation, though. Thanks, fellas. So one of the attendees made a nice comment on here. I'll let you react to it. He said looks like it would save us a lot of time and money on iterations and prototyping. Is that pretty typical of the results that your customers would see?
Absolutely. It in many cases eliminates the physical prototyping, and you're doing it on the screen.
Yep, sure.
Much less expensive.
So let me make, if you allow, let me make a comment on this. So this is the key value of this software. And let's say even in an everyday project where you more or less know what to do, you can save the iterations, and it can save you maybe $5,000 or $10,000. But what is even more important, using this software is like something like an insurance that you never have a catastrophe. So sometimes, so once a year or maybe each 2 years, you have a project and you iterate and iterate and iterate, and you don't come to the end in the real world. And this is so expensive. So we have a customer that spent in one case about 70,000 euros on tryout. And in simulation, we saw immediately that he should never have quoted for this project. So the simulation is something like an insurance that you don't have a catastrophe. So you have good saving in a normal project, and you don't have a disaster. This is the key value.
Thank you,
Terrific.
Luca.
Thanks. We do have some more questions coming in. Talk a little bit about, one of you explain the process for adding new material cards to the database. This particular viewer of the webinar today uses some unique materials. Niobium is one that he cites. So how do you add new materials to the database?
Gotcha. Yeah, I can actually show that on screen right now if you'd like. So what you can do is you can either start out with a material that may already exist inside a Stampack. Otherwise, you can always add something in from scratch. But let's take a look at that original 304 stainless we were using here. So what we can do is we could just simply copy that information over to our user database, and this is where you can set up whatever custom materials that you might have in real life. So here's that material here that we just copied over. You can go to edit this, and right in the software you can start making some changes if you have more of a specific yield stress, tensile stress, if you got any elongation percentages that you want to put in. So any of that information that you're being given from your vendors or that you're having done via other testing, you can always come right in here, very quick, very easy, add this in, and you can also save these databases out and share them with your coworkers.
And all in all, there are 570 materials included. And so it would be interesting to know what is the material of the person that raised the question, because with Inconel, titanium, copper, brass, stainless, aluminium, standards, cold rolled steel, hot rolled steel, high strength steel. So I think we cover really a good range. So I would be surprised if it's not included.
Okay. He specifically said niobium. You have niobium in there?
I apologize. I'm not fully familiar with the American names. So we have translations. So all the material cards have a US name, but I don't know it by heart. I'm sorry.
But please send us an email or give us a call, and we'd love to look into it for you.
Yep. Next question is, does the software work well for deep draw operations, and can it simulate breakaway on trimming operations? So deep draw and breakaway on trimming.
It's exceptional for deep drawn parts. As far as the break, it does not calculate the break in the thickness of the part. But for deep draw, that's as Luca says, it's home game. It's really, really well suited to ironing and the thinning that goes on in a deep drawn part. That's one of the biggest pluses with a solid.
Okay, good. How about limitations for part size or material thickness? Are there any limits there?
No, we have customers that have parts with thickness 0.01 millimeter. So this is a Swiss company that makes parts for watches. So extremely high precision stamping, and the thickest part we ever simulated was 18 millimeters. And let's say the standard stuff goes until 8 millimeter or 10 millimeter, I would say, though this is everyday's business. And part size, I think the part for the watch, it was 0.5 millimeter large, and the biggest part I ever saw on the screen was, I think, 5 meters. So in the end, it's all metal stamping. It doesn't matter.
Okay. All right, any more questions from our audience? The last question, I think, then would be related to training and how long it typically takes for users to get up to speed with the software. Ray?
Good question. Josh, you want to take that?
Yeah. So I actually do our training as well. For our training, it's just 12 hours that spans over 3 days. And as far as how quick that I've seen customers use it, very next week after training, I had a customer say that they took 2 separate projects that they had at their company, completely set everything up inside of Stampack, had it all working, and they never even needed to reach out to ask additional questions. It was just working right away for them just after that training. So as far as stand-up time, it's very, very quick.
Yeah, Josh has done a great job of doing a curriculum for us here in the U.S.
Fantastic. All right, well, that brings us to the end then. So again, thanks to everybody for attending. Thanks to Ray, Josh, and Dr. Hornung for presenting. You can close your browsers now, and wish everybody a great afternoon.